you. Welcome back, everyone, to the Brazilian Algebraic Geometry Seminar. Just completing 1 year of our meetings. Today it's my pleasure to introduce Aline Andrade from Universidade Federal Fluminense, Hooft. She'll talk about rank 3 instanton bundles on projective 3 space. Aline, please go ahead.
Thank you so much. I would like to thank the organizers for the invitation. It's a very good opportunity for me to talk a little bit about this work. Well, this work is a joint work with Danilo Santiago and Luis Sobral from Unicamp and Danilo Silva from Universidade Federal de Sergipe. So I will talk a little bit about instanton. So let me make some introduction here. So the instantons are pseudo-particle solutions of classical Yang-Mills equations. They awake a great interest in the mathematical and physical community since the 70s. These physical particles are associated with holomorphic bundles. So it's a natural link between mathematical physics and algebraic geometry. Well, the work that has been done involves the study of the moduli space and to study reducibility, the smoothness, and the spectral dimension. But since the 70s, it grows a lot, it evolves a lot, and we have a generalization of the definition of an instanton with the work on instanton sheets. We have other structures that we see on these instanton bundles. But one of the good things that we have is that the instanton bundles of rank 2 and second Chern class equals to n fulfills a reducible component of the moduli space of vector bundles. So these bundles appears naturally when we study the moduli space of vector bundles in general. So it's natural for us to see what happens when we work with higher rank. So as we see, as I talked before, we can add some structure of these bundles. So we can talk about orthogonal instanton bundles, symplectic instanton bundles, and a lot has been done in this sense. So our goal today is to work with the case of rank 3 on P3, okay? So first, just let me remind you, I cannot see you because I'm using my tablet. So if you have any question, please stop me and you can use your microphone, okay? So let's continue. So an instanton sheet on P3 is a torsion-free coherent sheet satisfying this following cohomology vanishing conditions, okay? The first Chern class is equal to 0, and its second Chern class is what we call the charge of the instanton, okay? If in addition, this torsion-free sheet is locally free, we call this an instanton bundle, okay? Well, we are trying to use these instantons the instantons to study the moduli space of vector bundles. So we have to introduce some other tools, okay? First of all, I would like to remind you the Hartree-Series correspondence theorem, okay? So let X be a smooth algebraic variety and Y be equal dimension 2 locally complete intersection subscheme. We will consider the normal bundle of Y on X and L a line bundle as well in X, okay? Such that we have this vanishing condition. Let me see, can I use my pointer? We have this vanishing condition over here, okay? Well, we will assume that this wedge power is generated by R-1 double sections. Remind that R is the dimension, it's the rank that the vector bundle that we want to define, okay? So there exists a rank R vector bundle such that this R wedge power is equals to our line bundle. And this guy has R-1 double sections, which dependence locus is Y, and we have this vanishing over here. And more, if this first cohomology is equals to 0, then F is unique up to isomorphism. So this theorem is very powerful because we associate locally complete intersection subschemes with vector of a algebraic right with bundles. In our case, we are working with locally complete intersection subschemes of codimension 2 on P3. It means curves. Okay. So the first result that we have in this direction is the following. So consider a node-degenerate locally complete intersection rational curve y on P3 of degree n plus 3 with n greater or equal to. Then the determinant is generated by two global sections, and if E1 is the corresponding rank 3 vector bundle given by this Chern correspondence, then E is an instanton bundle of charge n. And can you still hear me in a good sense? Because my neighbor is made some loud noises over here. I don't know if I can continue. So we have this association between locally complete intersection rational curves on P3 and instanton bundles of charge n. So what we do this. Jardine, Markusevich, and Tikhomirov give this characterization of the normal bundle. So we can check the conditions of the Chern correspondence in order to have the bundle EY in this sequence 1. Well, to see if this bundle is an instanton bundle is just to check the vanishing of the cohomologies. So it's not a difficult job. Okay, so we have node-degenerated local complete intersection rational curves with fixed degree associated with instanton bundles of fixed charge. Okay, so since we want to see if these instanton bundles, how they are related with the component of the moduli space of vector bundles, it's natural that we revisit the definition of which is a spectrum of a sheath. Okay, so to define the spectral, we have this theorem. We have if let F be rank R torsion-free sheath on P3 with generic splitting type A1 AR, and these integers respect this order, and let S be the dimension of this cohomology group. Then there exists a list of n integers Q1, Q2 to Qn, and K1, K2 to Kn, which also respect this order, which satisfy the following. They can use to compute the dimension of these twists of the bundle F. Okay, well, these integers that appears in this theorem has a specific name. They are called the spectrum of a sheath. And more, the amount of these integers is controlled by the second Chern class of our bundle, of our sheath. Okay, well, the spectrum, these integers, they had very good properties, and they help us to count the amount of components in the modular space, and to determine if a family of bundles it's in one or more of one component. Okay. Okay. So in our case over here, we will use this the spectrum to give a classification of instantons. So if F is a semi-stable rank 3 vector bundle and N is its second Chern class, then F is an instanton bundle if and only if the spectrum of the bundle is only made by zeros. Okay. So now we are trying to give the other way around. I give you a rational curve on P3, and then we obtain a vector bundle. So now we have the other way around. Given a bundle, we will have a curve, which is the following result. But to see that we have that, we need to see that we have some relation between the invariance of the vector bundle and the invariance of the curve. So let F be a rank 3 vector bundle in P3 with Chern class C1, C2, and C3, and let Y be its corresponding curve given by the Hartree-Serre response. Such that Y has degree D and arithmetic genus G. So the degree of the curve is given by the second Chern class of the bundle, and the genus is associated with this number, which depends on the Chern classes of our bundle. So with this, we have that given a rank 3 instanton bundle on P3 with Chern class N without global sections, and suppose that he has this twist has at least 2 global sections, then we have he is in this expansion, and more this Y, this rational curve on P3 has degree N plus 3. So indeed, if since that we have at least 2 global sections in this twisted, which are linear independent sections of F1, we can determine this exact sequence over here, and where Y is a locally complete intersection curve in P3. And the Chern classes of Fy, F1 are 3, N plus 3, and N plus 1. Then we can use the previous proposition to determine that D, the degree, is the second Chern class, and the genus is this number, which is 0. So Y is a rational curve of degree N plus 3. Okay, so I can take a rational curve and obtain an instanton bundle, and I can take a rank 3 instanton bundle and obtain a curve. This will be very useful for us in a few months. Okay. Let me just come back a little bit. So we have a rank 3 instanton bundle, and in this proposition, we need to have at least 2 global sections. So 2 is equal 3 minus 1, and instanton, which has for this first twisted at least R minus 1 global sections, has a specific name. They call it Hooft bundles. So a Hooft bundle is a rank R instanton bundle on P3, which has at least R minus 1 global sections in this twisted. Okay. Questions so far? Okay. So let Y on P3 be a node-generated rational smooth curve of degree N plus 3, and F be its corresponding rank 3 instanton bundle of charge N, given by the previous theorem. Then it is to see that F is a bundle, and so it fits in this follow exact sequence, and we have the following. Y, if Y is a node-generated rational smooth curve of degree N plus 3, and F its corresponding rank 3 Hooft bundle of charge N, if we have the vanish of the x of the curve, the ID of the curve, then we have this vanish for the x2 of the bundle. So this will be used in the future for us in order to see the smoothness of the point, to see that the Hooft bundle is a smooth point on the moduli space of bundles. Okay. the following result that we have is that the generic stable rank 3 Hooft bundle of charge n is a smooth point in the modular space of rank 3 vector bundles of Chern classes C1, C2, C3 equals to 0 and n 0. Well, this relation between these curves and these bundles, which also provide us a relation with reflexive sheaths, which as well are in correspondence with this fixed curve via the Chern correspondence. So we took Y, I'm sorry, on P3, a curve would satisfy the hypothesis of the Chern correspondence. Okay. If we have a rank 3 current sheaf on P3, then we have these equivalent conditions. F is a vector bundle, which is in correspondence with our curve via the Chern correspondence, if and only if F is in this extension, where E is a rank 2 reflexive sheaf, which also corresponds to Y. So we have a relation between vector bundles and rank 3 vector bundles. This is important to freeze, and rank 2 reflexive sheaths, both of them in correspondence with the same curve via the Chern correspondence. Okay. Well, this is in general for the bundles and the sheaths, but this relation over here give us more. When we focus on the case of charge 2, we have a one-to-one correspondence between pairs, where F is a charge 2 rank 3 stable instanton bundle on P3, and sigma is a global section of this first twist. So the charge 2 gives me the exact spot where the global sections will appear, which is in this case, in this first twist. Okay. This correspondence is with pairs E and C in C, where E is a normalized rank 2 stable reflexive sheaf on P3 with these given Chern classes, and key is this extension that we obtain in this previous theorem over here. So I have vector bundles of rank 3. In this case, we have a fixed charge, the charge 2, and we can relate with these pairs over here of extensions of reflexive sheaths and these reflexive sheaths. Well, this will be interesting for us because we are trying to study the moduli space of vector bundles, and we will do this via the moduli space of stable reflexive sheath, rank 2 stable reflexive sheaths that we have a good literature for that. Okay, so how we're going to do that? So we will try to study the family of rank 3 stable instanton bundles with charge 2 on P3 that I will call I2. And our goal is to prove that this family fulfills a irreducible component of the moduli space of rank 3 stable vector bundles on P3 of Chern classes 0 to 0. Okay. And we will use this correspondence that I given in the previous theorem. So let R be the moduli space of stable rank 2 reflexive sheaths with Chern classes -1, 3, 3. So we will use the universal bundle U, and by Cheng, R is a reducible rational variety of dimension 9 and 10. And we can consider the projection between P3R into the second coordinate. So for every point in the moduli space of rank 2 stable reflexive sheaths by the base change theorem for relative X sheaves, we have the following. So, these X1 sheaves obtained by the universal bundle over here are isomorphic to these X2Ys over here. And these guys we know that are isomorphic to these cohomologies over here. So also by chain, we have this vanishing of these guys for I equals to 0, 2, and 3. And by the local to global spectral sequence for X2 sheaves, one has that this X21 is isomorphic to H0, and therefore the dimension is 3. Okay, so we'll call by X this product between R and this X21. So each point in here parameterizes points E key, where key are extensions over here. So each point on P3 gives me a stable rank 2 reflexive sheath and a extension over here. And this is a irreducible variety of dimension 22. Okay. Well, now that we have that, I will consider a morphism map between X. Let me remind you who is X, is the stable rank 2 reflexive sheath with the extensions of the universal bundle over here. And so I will consider this map given by the composition and the correspondence that we have in the previous theorem. Well, that means the correspondence between pairs of reflexive sheaths and extensions and vector bundles and sections. And this projection onto the first coordinate, so onto bundles. Well, clearly these factorize to our instanton bundles. The images of the reflexive sheaths are instanton bundles, so this morphism phi factorizes through phi tilde. And additionally, for each bundle, for each instanton bundle, one has that the dimension of the inverse image is equals to amount of sections that we have on F1, so which in this case is 6. Thus, by our construction, this is a surjective open morphism of relative dimension 6, which implies that we have the dimension, and this is a irreducible variety of dimension 16. Okay, because we have 22 and the relative dimension is 6. So we have this following result. The family of stable rank 3 instanton bundles of charge 2 is reducible and has dimension 16. Well, you can see that I'm talking about the family of instanton bundles, but we are trying to see that this guy is in fact the diffusive component which is in fact the whole moduli space that we have. So we have the following. Every rank 3 stable vector bundle on P3 of Chern classes 0 to 0 is an instanton bundle. So we prove that the image of the morphism on the proof of the previous proposition is the instanton bundles. So now we are trying to prove that in fact all rank 3 stable vector bundle is a instanton bundle. So to do so, we will consider F and rank 3 stable vector bundle on 3 of Chern classes 0 to 0, and I will consider Q1, Q2, K1 and K2, it's a spectra. So by the properties of the spectra that I mentioned before, but I do not show you, but we have two possibilities over here. We have the possibility of the spectra will be 0, 0, or will be -1, 1. So it's by the first, one of the first propositions that I show you. If the first occurs, we have our result. So let's try to see that -1,1 is not admissible as a spectral for our rank 3 stable bundle on P3. Okay. So using the theorem which characterizes the spectrum of sheath, we can compute these dimensions of these twisted, and then we have these dimensions, H1 of F-2 and H2 of F-2 is equals to 1, and H2 of F1 is equals to 0. By the Heisenberg-Riemann-Roch formula, we have 6. So we have at least 6 global sections. And by the proposition 4, there exists a locally complete intersection rational quintic Y. So this is the proposition with we can identify bundles with curves, and the degrees and the degree and the genus of the curve are associated with the invariance of the bundle. So this is why we have a rational quintic, and that corresponds to our bundle. Okay. Well, by the theorem 2, it follows that F is an instanton bundle of charge 2, but since we have that, we cannot have that the dimension of F-1 is equal to 2, which contradicts the dimensions that we have in 3. Okay, so we assume that this vector is -1 and 1, and we gave a contradiction. So all rank 3 stable vector bundle in P3 of Chern classes 0 to 0 are in fact instanton bundles. So we have this, the moduli space of rank 3 stable vector bundles on P3 with Chern classes 0 to 0 is a irreducible and generically smooth of dimension 16. So to prove this theorem, it's just to glue together all the results that I show you so far. So by previous proposition, we have that B0 to 0, it's in fact the family of the instantons of charge 2, and we also see that this family is irreducible and of dimension 16. And given a point on the family, and this is a generic Hooft instanton bundle, so we know that the x2 is equal to 0. And additionally, we have that the dimension is 16, which coincides with the dimension of y2 computed on the previous theorem. So this implies that the generic Hooft instanton bundle is a smooth point on B0 to 0. So this is the sum of the papers that we use to prove these results. And thank you so much for your attention.
Thank you, Aline. Are there any questions?
I have a quick one.
Yes, go ahead.
At the beginning, at some point where she first stated the correspondence between bundles and curves, the Hartson correspondence. Yeah. At some point, you wrote a relation between the normal bundle N and the line bundle on the curve.
Okay.
Yeah. No, it's the previous one.
This one?
Oh,
or
the next one.
The next
it's the one where you have the
yes,
relation. This one. You write NYP3, which is rank 2, equal to OI, a multiple of a point, which is rank 1. So maybe there is a wedge missing in the left.
Probably. in which one I cannot see, but I assume that is Israel.
Yeah, so you write NYP3 equal to
Yeah.
OY, a multiple of a point.
Yes.
NY is rank 2. It's the normal bundle of a curve in P3. OY is a line bundle on the curve, so it's rank 1.
But this is the wedge 2. It's wedge 2, wedge R of a rank R bundle.
There's
so
a
this
wedge
is a line bundle.
There is a wedge 2 missing in the left-hand side, is that?
Yes, yes.
But then the formula for wedge 2 that you write in the next line is not compatible with the previous one.
Let me see.
So maybe the right-hand side is a sum of 2 copies. If the right-hand side were a sum of 2 copies of OY, 2n plus 1, then the wedge would be the one that you wrote in the next line.
Yeah, I think that's it. It's 2 copies.
Yeah, 2 copies. Ah, okay.
So let's.
I can check, but I believe that. But well, it's the result from Marcos.
No, it's not. It's in one of my papers, but it was not me that I. It's not.
So I have another a couple of Kabbalistic remarks. So you have dimension 16 and 19. Anyone in this audience will think of examples of other moduli spaces with this dimension. So 19, for instance, could be just cubics in P3, as well as, say, quartic mod isomorphism. Quartic surface mod isomorphism, that's dimension 19.
Mm-hmm.
So is there any correspondence whatsoever between this moduli space and either the space of cubic surfaces or K3 quartics?
Well, I don't know. I don't know. The only correspondence that with curves that appears in this study was this one given by the Hartmann-Serre correspondence, so which is with quintiles.
Yeah. So 16, I guess, is a dimension of rational quartics, if I'm not mistaken. And at some point you have a moduli space which is of dimension 16 as well.
Yes, it's the one of the instantons.
Anyway, it's just because I have how do you say an infatuation for numbers.
We all have.
Yeah, the rational curves that appear here, they are degree 5, right?
Yes.
Oh,
Rank 2 instantons have to do with rational curves of degree 5.
Yeah, but 16 is dimension of degree 4, I guess.
Yeah, yeah.
I think it's 4D, right? The
Yes,
expected dimension of moduli of curves of degree D. Rational curves, I think it's 4D as well.
Mm-hmm.
Wait, no, I think maybe it's 4D minus 4 because you have the polynomials and then you projectivize and then you have the 3 automorphisms of the P1 that you have to subtract.
Because twisted cubics is 12, which is 4 times 3.
Oh yes, right. Yeah, okay. No, you're right. Right, of course, it's 4D plus 4 minus 4. Yes.
Yeah.
More questions or comments for Aline?
So I'm just wondering, is there any chance of proving similar results for even slightly more complicated bases? Like if you looked at a cubic, if you looked at a quartic in P4, could you maybe prove results on vector bundles on that?
with this kind of approach that we have here, it's a little bit difficult because let me come back over here. In the general case, for any charge, we have this correspondence over here between vector bundles and these tensions with these rank 2 reflexive sheaths. Well, when we see what happens with the charge, since the charge 3, 4, then on, we don't have a control where it will appear, these global sections that we have here. So this technique over here is, I don't know if we can use as well, because for in the case of charge 3, for instance, and the rank 2 stable reflexive shift that we'll have will be of Chern classes -1, 4, 4. And then we don't have a classification. We don't have the study of stable reflexive shifts. So these techniques that we do here, I believe that we cannot continue and use for the study of associate with other curves, as you suggest.
But I guess the question was about bundles in higher dimension, right?
Well,
so,
no, not higher dimension, but just slightly more complicated threefolds, like other final threefolds, like the Gordic.
Oh,
like,
yes.
Sorry, like the quadric, not the Gordic.
So instead of P3, considering a quadric.
Okay. Well, I do not try, but I don't know if we can do this, because work with instanton is good because we work, they are well behaved because we work with cohomological conditions. So I think that it depends. It depends a lot on how we have these conditions, and because the vanish of some of these conditions of the instant, which will give us these expansions. So I don't know. It depends.
Thank you.
Welcome.
Yeah, there is actually a notion, right? So there are definitions of instanton bundles on other threefolds like quadrics and cubics and so on. And people have studied rank 2 instantons on quadrics and cubics. So maybe some of this can be adapted to these other more complicated curves as well. Yeah, but there's no literature about it actually. But my question for you, Aline, is when you make this correspondence between the Hooft bundles and the rational curves, are the Hooft bundles stable in the rank 3 case, say?
Yes.
Yes. Okay.
Yes, they are stable. I don't know. Let me see. I believe that the result of the Hooft, yes, the generic is stable Hooft bundles.
Okay, good. Thank you. Are there more questions?
Hi, I have a question. It's more of a beginner's question, let's say, more general, like because of the vocabulary in this, like instanton bundles and charge reminds me a lot of physics. So like I suppose there is a connection to physics, but I don't know enough to know like what it is. So if anyone could talk a little bit about that, you know, like what's the connection to physics that justifies the use of those words?
Well, you're welcome. So as I mentioned in the beginning, so let me come back a little bit. I believe that I put here. So the instantons in physics are the pseudo-particle solutions of the Yang-Mills equation. So they are holomorphic rank 2 bundles on CP3. So we have the AGA-GEM constructors in the 7th, which studies a lot these guys, but we also have a generalization of these bundles. So these guys over here that are defined by these cohomological conditions, when we are on P3 and we are studying rank 2, they are in fact the same ones. They are in relation to the same ones of physics. So more than that, I don't know if I can give you anything of how can we, for instance, apply our result on that. But we have this relation. They call instanton bundles and instanton sheaves because they came exactly from the study of the solutions of the English equations. In the beginning of the 7th, I believe that they also, in some of the papers, if you look, we will now see charge, or we'll see quantum number, which I believe it's what physics is.
More questions? If not, let's thank Aline again for her talk. That's all for today. We'll come back next Wednesday for a talk by Alex Massarinti. Thank you very much, everyone, for attending.
Thank you so much.